In the next part of this video, covering the document that's on D2L, I want to look at a formulation of Newton's laws in terms of momentum and energy. And this, I believe you covered this in your introductory physics course, but maybe not to the extent and maybe not with the emphasis that we are going to do here. When we move over to quantum mechanics, we're going to express things more in terms of not forces influencing the motion of a particle, but rather energy, particularly potential energy. So I just want to go over restating Newton's laws in terms of variables momentum and energy instead of velocity and force. So if you're following along, you'll see the definition of momentum is mass times velocity, and universally we give it the symbol P. So we write P equals mass times velocity. And then we also talk about kinetic energy. Kinetic energy is pretty much universally in this course given the symbol T. You might want to make a note of that, capital T as opposed to small t for time. And T, as you probably already know, is 1/2 mv squared, which you can pretty trivially write as p squared over 2m. I will leave it to you to prove that. Okay, now the forces acting on a particle are expressed in terms of the potential energy, and so specifically corresponding to every force there's a potential energy function, so the potential energy is indicated by the symbol V. So V is a function of x. I remind you we're just going in one dimension now, and so V is potential energy. Okay, and then the force in terms of the potential energy, again for one dimension, the force is equal to the negative derivative of V with respect to x. So this simply expresses the intuitive result that a particle experiences a force pushing it to lower energy, and that this force depends on the slope of the potential energy function as a function of x. So for example, say, draw a little graph here, we will say potential energy, so we'll put potential energy on this axis, x on this axis, and here is a potential energy function. Now, at this point, the particle at this point experiences a force in this direction proportional to the slope. And so that seems kind of reasonable. Just imagine a little ball or something rolling on a surface, and the ball will tend to roll downhill. At this point, the particle will experience a potential energy function also in the same direction, but it'll be smaller because the slope is smaller. At this point, the particle experiences a potential energy, experiences a force in this direction, And down here, right there, the particle is at equilibrium and force is 0. Okay. Now, it should be emphasized that not all forces can be expressed this way. For example, frictional forces depend on velocity. But for the problems that we're going to encounter, which are at a microscopic level, there will be no frictional forces. And so all the forces that we know about can be thought of as the result of a potential energy function. So, when I have this, with these definitions of potential energy and these definitions of potential energy and momentum, we can show that Newton's law, which we write this way, is equivalent to this formulation, minus dV dx, the derivative of potential energy with respect to position, is equal to dP dt, the derivative of momentum with respect to time. And I will leave it to you to show that these two are exactly equivalent, so that they're equivalent ways of stating the same thing. As long as the force can be regarded to be the result of a potential energy function. As an aside, such forces, the forces that can be thought of as a result of a potential energy function are said to be conservative forces. And something that I will not show, but again, you should be able to do this, I won't ask you to, but that when motion comes strictly from these forces, the total energy, E equals T plus V, is conserved. And by that I mean this is constant, and for any particular problem I work through what happens with the motion, I will find T as a function of time, V as a function of time, but their sum does not depend on time. This should be the familiar conservation of energy. And so remember, conservation of energy for macroscopic particles doesn't work if you include frictional forces. A moving particle eventually comes to a stop. But for microscopic particles that we're going to talk about where there is no friction, total energy is conserved. Okay, a little bit about notation and what happens when we go to 3 dimensions. Okay, just a minute. In 3 dimensions, we can have the total kinetic energy will come from motion in 3 directions. So we write in general instead of just, again we're going to use momentum as a variable. Instead of just p squared over t, we will write 1 over 2m px squared. So that includes the kinetic energy due to motion in x direction, py squared plus pz squared. Okay, and if you know a little bit of vector notation, and things like dot products and so forth, you you should be able to see that this is simply P, vector P, dot P. The dot product of P with itself. The dot product of two vectors gives me a number. And then this is often, even when I'm talking about 3 dimensions, this is often simply written as P squared. When I write the square of some vector quantity like this, I understand it to be the dot product with itself. So, T is P squared over 2m. Then I can... Okay, then how about potential energy? So potential energy in 3 dimensions is a function of it's a function of position, or a function of x, y, and z. Okay. We introduce a notation here called the gradient. So the gradient of v. So v is just a number which is a function of x, y, and z. The gradient of v gives me a vector at every position, and the gradient of v is indicated by this upside down delta. Put an arrow above it to remind us that it's a vector v. It is defined as the vector dv dx dv dy and dv dz. So now properly I should be using partial derivatives for this, but I think you'll understand. So how does v change when I change x? How does v change when I change y? And how does v change when I change z? It's got 3 components. As a vector, it points in the direction of maximum change. Let me do a little bit more explanation of what the gradient of v is, what the gradient means. So suppose instead of 3 dimensions we have 2 dimensions, and you might be familiar. And so I have something that's a function of some function that gives me a number for every position on the plane. And you might be familiar with topographical maps. That's a way of indicating that indicating elevation in on a map of the Earth's surface. In a topographical map, what I do is I join by lines. Or curves every point that is at the same elevation. So all these points are at the same elevation, say 1,000 feet above sea level. All these points are at a higher elevation, say 1,100 feet above sea level. And say all these points are at still higher elevation. And here this is kind of this would be a topographical map of something that is a hill. The top of the hill is right here in the middle, where I'm putting the dot. And what is the gradient of this function? The gradient is simply it tells me how steep the hill is at any particular point. Let me add a couple more. If it's particularly steep, the gradient lines will become the topographical lines will become closer together. And the gradient at any particular point is a vector whose magnitude tells me what the slope is. In other words, the steeper the hill, the higher the slope, and whose direction tells me which direction is directly uphill. So like at the point I'm indicating here, the gradient is a vector in that direction. Okay? And at a point over here, the gradient is a vector in this direction, but it's not as big because the hill isn't as steep there. At the very top, right up here, I'll indicate that. Right up there, the gradient of this function would be 0. So at a maximum or a minimum, the gradient is 0. At any point, the gradient is a vector that points directly uphill, whose magnitude tells me how steep it is. So that's kind of a picture of what the gradient is. I won't prove to you that that's what how this comes out, but we'll just take my word for it that this definition of the gradient gives me this qualitative picture. Now, when generalized, so Newton's law generalized to 3 dimensions can be simply written this. Okay, so remember, remind you one dimension, minus dv dx, that's the force, is equal to dp dt. This is the force. The left-hand side is the force, the right-hand side is the acceleration. As of when I write this in vector form, I have minus the gradient of v, which is a vector, is equal to dp dt. Okay? The minus indicates that, so this left-hand side is the force, it's a force vector, and this right-hand side is mass times acceleration. And the minus sign indicates that the force points in the direction of moving the particle downhill in kinetic energy. Okay, I think that's it. I think that's it, and I will leave it at there for now. There are a couple of problems, if you're following along, a couple of problems just asking you to kind of show that these things work for the gravitational problem indicated earlier. And also showing, for that gravitational problem, show that the energy, the total energy, kinetic plus potential, is a constant. And what that means is you come up with a function for it as a function for each, you come up with an expression for each as a function of time, and you combine the two and you find that time does not appear in the result. So in other words, if we do E equals t plus v, t will depend on time, v will depend on time, but E will not depend on time. Okay, that's it. I think that's the end of my lecture for the classical mechanics review.